Okay, so in this movie clip, let me describe let me show you how to derive the ideal diode equation of PN junction diode. So as the very first step to derive the current voltage characteristic or current voltage analytical equation, so let's suppose that a certain amount of forward bias, that is V sub A is higher than 0, is applied across PN diode. Then, as you can imagine, the potential barrier height from the perspective of majority carriers in P side or N side would diffuse into the other side across the junction. Okay, so because of the forward bias, the potential barrier height should be reduced and lowered. Then what would be happened? What kind of mechanism, what kind of events would be followed? So let me draw the cross-sectional view of PN diode here, P and N. So here is a physical contact metallurgical junction. So the majority carrier holds, now the forward bias has been applied. So the energy barrier height has been lowered. So majority carriers holes and electrons are ready and more likely to move into the other side like that. Then once hole has been arrived in the N-side region beyond the depletion layer width, okay, once hole is arrived at the N-side, then this hole would be treated as minority carriers in the N-side because N-side has a bunch of abundant number of electrons. The hole is likely to recombine with majority carriers, which is electron in N-side. Similarly, once because of the forward bias, the energy barrier height has been lowered and electrons originally majority carriers in the N side, but it is now arrived at the P side. Then this electron would be treated and worked as minority carriers, and this is more likely to recombine with majority carriers, which is a hole in P side. Okay, then this event is named as minority carrier injection, because from the perspective of an N side, the hole, which is the minority carrier has been injected from the P side. What about this electron? Because under forward bias, the energy barrier height has been lowered and the electron has been injected from the N side into the P side. So this, from the perspective of P side, minority carriers, electrons are injected into the P side. So we can say and we can claim that minority carriers are injected into the P side and N side. But herein I have used the quasi-neutral reasons. What are they? So let me redraw the cross-sectional view of PN diode, and here the depletion layer existing. So beyond the depletion layer, this area and that area is named as quasi-neutral region. So simply Q and R. Okay. So we can claim that we can understand that the minority carriers from N to P and from P to N, right? More specifically, holes from P to N, electrons from N to P are injected into the quasi-neutral regions. So let's write down some variables and symbols to describe this minority carrier injection event. So previously I said the electron concentration in the P side, N sub P. The meaning of subscript indicates the region, and N indicates the electron concentration. So N sub P indicates the minority carrier concentration in the P side. And NP naught, what is this? So this naught indicates a thermal equilibrium. So without naught, the N sub P indicates the electron concentration in the P side at non-zero condition. However, once I write down N sub P naught means electron concentration in the P side at thermal equilibrium. Okay, so these two values should be different from each other. And from this, we can write down this equation, excess carrier concentration. Okay, excess carrier concentration. Okay, so excess carrier concentration has been defined as how much additional carriers are injected with respect to the carrier's concentration at thermal equilibrium. So n sub p minus n sub p naught. So this difference would be denoted as delta n sub p, and this delta n sub p as has been understood as the excess carrier concentration. Okay, so going back to the p-n junction diode under forward bias, now the minority carriers are injected from p to n, so or n to p. So once the electron has been injected into the p side, then in the p side, the minority carrier concentration would be affected by this injection. So originally there is a certain amount of electrons, but because of this carrier injection, the n sub p electron concentration in p side would be disturbed away from the n sub p naught. Okay, so this difference is denoted as delta sub p np, and this delta np should be positive because n sub p is definitely higher than n sub p naught because the more electron has been added up to the p side because of this injection. Okay, so similarly, the hole has been injected from P to N, so the minority carrier concentration in N side denoted as P sub N. And at thermal equilibrium, the hole concentration in the N side at thermal equilibrium is denoted as P sub N naught. So Pn must be higher than P sub N naught because why? Why is that? Because more hole has been added up, injected into the N side, so P sub N is higher than P sub N naught. So now, if I calculate the delta P sub n is P sub n minus P sub n naught, now this is higher than that. So definitely delta P sub n is higher than 0. So these two has been well describing what would be happened across PN diode under forward bias. Okay. Then the next question is, let me redraw the PN junction, the cross-sectional view of PN diode again. This is a depletion layer width. Okay, so once hole has been injected into the N side, then what is the main mechanism? How those injected holes would move toward the edge of the quasi-neutral region of N side? What kind of mechanism would be dominant? So previously I said this. This is a cross-sectional view of the PN diode, and now I have applied certain amount of voltage. And this applied voltage has been 100% well delivered to the depletion layer. So junction voltage drop is almost equal to the applied voltage. That means no voltage, no voltage drop in quasi-neutral region. Okay, so that means this potential value and that potential value has no difference. That means delta V is 0. So dBdx is minus E electric field, and that is 0. That means in the quasi-neutral region there is no electric field. No electric field means no drift. Okay, so drift, you know the meaning of the drift, how the electrons and holes are moving in a silicon material. There are three mechanisms, right? DDR, remember the DDR, right? Drift, diffusion, recombination, and generation. So just removing the G and DDR. Okay, so when we are talking about the first D, drift, the electric field is necessary. But in this QNR region, of course, in this QNR, in the N side as well, there is no electric field. Hence, the drift mechanism can never be available, never be used to explain how the holes, injected holes are moving toward the edge of the N side. Then another D, diffusion, would be the right answer and right choice, how the injected holes would move and move towards the edge of the N side. So as described here, minority carriers diffuse instead of drift. Diffuse in the quasi-neutral regions, but as well as recombining with majority carriers. So if you imagine how many holes and electrons are uh, annihilated or removed and killed by and recombined with majority carriers. Let me see, where's my pen? Okay, here. The hole is now injected here. So many holes are available near the edge of the depletion layer width. However, if I move one step more forward, then think about how many holes would be alive. While the hole is moving by one step, then part of the holes would be recombined with electrons. So suppose that there is 100 holes injected, but one step more, only 50 left behind. Only left is available. Rest of the half, 50 holes are already recombined with electrons. In other words, they are killed. Okay, so as moving forward and forward, the total number of holes would be decreased. Why is that? Because the N side has abundant number of electrons available, and that electron would like to recombine with holes, which is injected from the P side. Okay, so if I draw, let me draw this x-axis, and this is the edge of the depletion layer on the N side, and well, actually this is another axis. Okay, and x prime, and x-axis. So this x-axis has been originally used while I was explaining the p-n junction theory, and here the physical contact metallurgical junction is denoted placed at x of 0, and from here to here indicates the depletion layer, and from here to here is x sub n. But in the new coordinate, this is another new origin, and here that is minus xp, but I'm going to use another new x coordinate for the p side q and r. So this is another origin point from the perspective of x2 prime x-axis. Okay, so once hole has been injected from the p to n side, uh, let's draw the excess carrier concentration. So delta p sub no, delta p sub n, yeah, hole concentration in the n side. Okay, so as I told you, the holes, injected holes, would like to recombine with majority carriers in n side, which is electrons. So the excess carrier concentration would decrease like that, but it should be decreased at an exponential pace because the holes are decaying at an exponential pace, because the delta p sub n divided by the x is proportional to the how much injected holes are available. So using this first order differentiation, you may expect the delta p sub n would exponentially decreasing. So more details would be studied in the upcoming lecture note, but don't worry too much about it. And let's write down the delta n sub p in the QNR region of p side again on the left hand side. So electrons are now injected from n to p side, and many electrons are available. However, in the QNR of p side, many holes are there. So holes and electrons would be recombined together. So delta n sub p, the value of delta sub np would be exponentially decaying down. So in the end, all the injected electrons would be annihilated with holes in the p side. Okay, so if you draw the delta excess carrier concentration on y-axis and along the x direction, you may expect that delta p sub n would in the end asymptotically going and approach to the zero value. In other words, p sub n is in the end equal to the p sub n naught, because it is approaching to the thermal equilibrium state. Okay, so that's all for the how the minority carriers are diffused into the other side and how they are annihilated with the majority carriers. So now we are almost ready to write down the equation for current across the p-n junction diode. So electron and holes are both carriers are well associated and used to explain how much current density has been current has been formed across the PN diode. So as we have learned here, the electron current density and hole current density, by summing up those two terms, we're gonna build up with total current density. And previously I mentioned that electron current density can be built with two components, one of which is drift current density, and the other of which is the diffusion current density. So here the current, you know the Ohm's law, right? J, the total drift current density, J, J is conductivity times electric field. This is identical to the Ohm's law. I is equal to 1 over R times V. If you missed it, how to understand it, please drop by my office. Then I would be welcome uh, to explain it. And second term is indicating the diffusion current density. And herein I have plugged in the, instead of N, excess carrier density N is N minus N naught. So if uh, we are talking about in the P side, right? So let me denote the QNR region P. So delta MP is defined as MP minus MP naught. And where is it? So if you plug in here, this value, so MP is equal to NP naught plus delta NP. However, this NP naught is always constant. So if I take a derivative, this guy would be removed so that NP would be replaced with a delta NP. So that is the reason why instead of N, delta N has been used in this equation. So we almost ready to complete and build up the total current density throughout the PN junction diode. So for a given forward bias V, the current voltage, no, the value of a current has been set. So 1-1 matching should be uh, should we should expect the 1-1 matching for a given voltage value. A single value of the current has been obtained. In other words, using oscillator and probe tips, if you have a chance to measure the current voltage characteristic of PN diode for a given certain voltage, the current value is single valued. Okay, so that means a total current measured throughout the PN diode is uh, determined by the voltage that you have applied. But the more physics complicated physics would be existing. So let me get back to you sooner or later. So please take a moment and 1 minute break time. So I will get back to you soon. So let me see here. 1 second.